Welcome to Chapter 4, Applications of Differentiation. We're going to look at Section 3, how derivatives affect the shape of a graph. And in this video, I am going to, as I have done in previous videos, walk you through the slides that were provided by Stewart in Calculus Early Transcendentals, 8th edition. And I'm going to make some comments and draw some little diagrams and stuff on these slides. And after we're done going through the slides, I have a couple of example problems that I have chosen from a homework assignment that I'm going to be assigning to my students. So I will hand write out solutions to those problems after we go through these slides. So first, what does the derivative say about the function? And if we look at Figure 1, which is in blue, we have a function that's drawn here. And these red lines that we see as tangent lines are indeed that. These are tangent lines. And those three tangent lines between A and B have a positive slope. And these tangent lines that are drawn over here also have a positive slope. And when a tangent line has a positive slope, and when I say slope, remember that that is directly related to the first derivative of our function, dy over dx, rise over run, change in y over change in x. The slope of these tangent lines is the rate of change of the curve at those individual points. And since all of these tangent lines have a positive slope, and all of these tangent lines have a positive slope, we can say that the function in blue is increasing on those two intervals. And in fact, that's what the slide tells us here, is that between A and B and between C and D, the tangent lines have a positive slope, so we know that the first derivative of the function is greater than 0. Those are synonymous. Slope, first derivative, positive means it's greater than 0. And between B and C, on the previous slide, we saw that the tangent lines had a negative slope, which means that the function is decreasing on that interval. So it decreases when your first derivative is negative because this is the slope of your function. In order to prove this is always the case, we use the mean value theorem. I'm not going to focus on proofs for the most part in my videos. Occasionally I might make some comments on them, but I don't want to get too tied up in proving. I want to focus my attention on helping you hopefully make some connections between the conceptual ideas about what's going on here and the actual mechanical processes and the algebra, so to speak, of solving some of these problems. So for the moment, let's just focus on the fact that there's an increasing, decreasing test, which the author is going to refer to as the ID test. I believe that's how he writes it. And what that says is that if the first derivative is greater than 0, in other words, if the slope of the tangent lines to a curve on an entire interval are greater than 0, then we're going to say that the function is increasing on that interval. And similarly for your first derivative being negative. Your first derivative being negative. It's going to be very interesting. You know, this is an x value, which means that this is a y value. So, and we're going to see this in a moment, if we were to graph f prime of x, your first derivative as a function, the x values are still going in, but the y values that come out are going to be representing the slope of tangent lines. And that's going to be very interesting to see graphically. Okay, example number 1, we're being given a function here, and we want to figure out where it's increasing and decreasing. Or we could even say when, instead of where. We could say when is it increasing and decreasing. And the answer to the question of when is normally how I like to phrase it, is we're going to be answering using x values, or portions of the x-axis, groups of x values. So first of all, the author has taken the first derivative of the function for us, and here it is, and then it's been factored into these three factors, the 12x, the x minus 2, and the x plus 1. And we're going to use that ID test, that increasing, decreasing test, in order to figure out where our first derivative is greater than 0 and where it's less than 0 in order to answer the question, where is it increasing and decreasing? If it's not increasing, if the function isn't increasing, if it's not going uphill, and it's not decreasing or going downhill, where is it? What's happening? What if the first derivative is 0? Then, as I like to say, you are either at the top of a hill or the bottom of a valley, and you're neither increasing nor decreasing. And it's those times that are going to help us chop up the x-axis into, in this case, 4 different intervals. And we're going to make a statement about whether or not the function is increasing or decreasing on each of those 4 different intervals. How are we going to go about doing that? We're going to figure out if we choose an x value that is on this interval, or on this interval, or on this interval, or somewhere on this interval. If we take an x value from one of those 4 intervals and we plug it into f prime of x, our first derivative function, we want to know, is it going to turn out that the first derivative ends up being positive or ends up being negative? Is there an organized way in order to go about making those determinations? Yes. Your author recommends using a table like this and selecting, for example, an x value that's less than -1, in other words, on the number line to the left of -1, and instead of plugging, an x value of -2, for example, plugging that into the function itself, the author says, why don't you plug it into the 3 factors that make up the function? So let's do that. For example, let's use an x value of -2. What's -2? What's -2 times 12? I don't even care. What I care about is that it's a negative number. And what about -2 minus 2? That's going to be a negative number also. And -2 plus 1, still going to be a negative. Great, when I take those 3 factors and I multiply them all together, what am I going to get? You mean, what am I going to get when I take a negative? Why didn't that work? I'll get there. You mean, what do I get when I take a negative times a negative times a negative? Well, I'm going to get a negative number. So when I choose an x value from this interval, the first derivative of my function is going to be negative. And what does it mean when the first derivative is negative? It means that your function is decreasing. Where is it decreasing? Or as I like to say, when is it decreasing? In this case, it's decreasing on that interval where your x values are less than -1. And then we keep going through that process over and over again, selecting x values from different intervals and plugging them into, one at a time, into these factors of the f prime function, and then making our statements about whether or not the function's increasing or decreasing on that interval. So that is the process. And if you take the information that we were seeing on the previous chart and you compare it to figure 2, which is the graph of the original function, you'll see that our conclusions were correct. The function was decreasing anywhere your x values were less than -1. It was increasing from -1 to 0, decreasing where your x values went from 0 to +2, and increasing everywhere your x values were greater than +2. We're looking at multiple things on this graph as I'm drawing these blue arrows. I'm looking at the red curve I'm looking at when on the red curve am I. First I was looking at my red curve when I was to the left of an x-coordinate of -1. In other words, when my x values were less than -1. And then we went in and we looked at this portion, and then we looked at this portion, and then we looked at when is this part of the graph happening? It's happening when my x values are greater than 3. Sorry, greater than 2. And that was supposed to be in a different color. I don't like when my tablet tries to boss me around. There we go, it's in green. That happened when our x values were greater than +2. So we're keeping our eye on slopes of tangent lines and on x-coordinates. Local extreme values. We've talked about extremes and extrema in the past. That's not supposed to be drawing. Still not supposed to be drawing. There we go. Local extreme values. So in figure 2, f of 0 is equal to 5. And in fact, that is true. Let me get rid of all of this so we can have a new conversation using the same diagram. So we're talking about this point right here, 0, 5. And this is just distracting. That's me being neurotic. I have to erase those. There we go. So in figure 2, we just confirmed that f of 0 is equal to 5 and that it was a local maximum. Why is it a local maximum? Because of our function increasing on the interval that was to the left of it and decreasing to the right of it. Or in terms of derivatives, our first derivative was greater than 0 or positive to the left of that point, 0, 5. And our derivative, or the slope, was negative to the right of that point, 0, 5. So again, we're going uphill here, which is a positive slope. And to the right of that point, we were just saying that the first derivative, or the slope of the tangent lines, are negative to the right of that point. Well, if I have to go uphill to get here and downhill thereafter, I must have sort of hit a crest or popped over the top of a hill. In other words, the sign of f prime changes from positive to negative at 0. In other words, when x was equal to 0. So we went from x values that were negative. My x value is -1, and it's getting closer to an x value of 0, closer to an x value of 0. And then here, I hit an x value of 0, and what is the slope of my tangent line at the point where x is equal to 0? My slope is equal to 0. This is the x-coordinate of that point. This is the slope of the tangent line at that point. Here, my slope was positive. Here, my slope is negative. And here, the slope was equal to 0. So again, we've changed from positive to negative. And what happened when we changed from positive to negative? The slope was 0. The slope changed from positive to negative at that point right at the top of the hill, which just so happened to be a point that had an x-coordinate of 0. A lot of zeros right there. Don't love that. Don't worry. We're going to talk about other points, maximums and minimums that don't have x-coordinates of 0. Okay, so the first derivative test. If c is a critical number of a continuous function, so if the first derivative equals 0, then we've got a point that has an x-coordinate, and we're going to say that the x-coordinate there is c. And if the first derivative changes from positive to negative at c, then we're going to have a local maximum there. And if we're changing from negative to positive, then we're going to have a local minimum. Slope here, negative. Slope here, positive. Slope here, 0. So when we change from a negative slope to a positive slope, where are we? We're at a low point, we're at a minimum. Okay, that's what's being articulated here in part B, a local minimum. And if f prime, so we're looking at part C now, if f prime is positive to the left and to the right of a point, or if it's negative to the left and to the right of a point, then we don't have a local maximum or a minimum at that point. What does that look like? Let me just pop down here. It looks like this. You'll notice that the slope of the tangent line here is positive, and here it's positive, and in fact here it's positive, and here it's positive. Here it's 0. Slope of the tangent line there was 0. But it's positive to the left, it's positive to the right. Is this point right here, does that constitute a maximum or a minimum? Definitely not. It's not at the top of a hill, it's not at the bottom of a valley, therefore it's not a max or a min. Same situation here, these are just visual representations of what we were seeing 2 slides up from here. This point right here, slope of the tangent line, 0. To the left of that point, slope of the tangent line's negative. To the right of this point, slope of the tangent line's still negative. Negative to the left, negative to the right, therefore this point is not a max or a min. Whew. Okay, I'm really trying to keep trucking through this stuff so that it doesn't take me forever to go through these slides, but I do like to make sure that I'm giving you a thorough description to try to make sure that everybody's on board. Okay, what are we seeing here? The first derivative test is a consequence of the increasing-decreasing test. So now we're saying there's a new test, a first derivative test. In part A, for instance, the sign of f prime changes from positive to negative at C. Here we are changing from positive to negative at this point, which has an x-coordinate of C. It follows, therefore, that f has a local maximum at C. And indeed, this point right here is a maximum. You're at the top of the hill. I really agree with this. Visualizing diagrams as frequently as possible is going to help us determine what's happening, better understand what's happening. Oh, and this was just another depiction of our slope changing from negative to positive. Therefore, the point where that change happens, where the slope of the tangent line was equal to 0, that point must be a local minimum. Local extreme values, we talked about what's happening on that slide already, and then example number 3 wants us to find the local max and min of this function. How do we do that? Well, first of all, notice that we're only going to be operating on a particular interval, which is a good thing because this graph goes on forever and ever, working with the sine function. And the beginning of the solution process requires us to take the first derivative of the original function. The author has done that for us. And then, as we try to chop up the x-axis or decide what intervals we're going to be examining, we need to take the first derivative of our function and set it equal to 0. And when we do that, when we take this function right here and we set it equal to 0 and we solve it, we find this statement. Subtracting 1 from both sides, dividing both sides by 2. And the solutions to that statement on this interval are 2 pi over 3 and 4 pi over 3. So that's what's going to allow us to chop up our x-axis, so to speak, or the interval that we're working with from 0 to 2 pi. So here's the 0, and here's the 2 pi, and we're working with the values that are between there. And the 2 pi and 4 pi over 3 are coming in here in order to help us chop up the interval. And the last time we worked with a table like this, there were a bunch of columns on here. There were a bunch of columns, and we had minus signs and plus signs in here, and then this was f prime of x. This one's a lot simpler looking. Why is that? Because g prime only has one factor, 1 plus 2 cosine x. So a lot easier for us to do our testing. So if we were to grab an x value out of this interval, plug it into our first derivative function, it would turn out to be positive. Therefore, our function g will be increasing on that interval. Similarly, if we grab an x value out of this interval and we plug it into the g prime function, we're going to get a negative value for g prime. G prime is the slope. If the slope is negative, we must be going downhill. In other words, it's decreasing. The original function g is decreasing on that interval. Same kind of a conversation here. Leads us to the conclusion that it's increasing on that interval. So that's the process that you want to go through, even if you format your process differently than making that table. Continuing on in the conversation about that same function g of x, because g prime changes from positive to negative at 2 pi over 3, the first derivative test tells us there must be a local maximum there, right? Because we were going uphill and then we transitioned to going downhill, positive slope to negative slope. We must be at the top of a hill. That's a local maximum. We can take the x value of that local maximum, plug it into our original function, determine the corresponding y value, and that y value will be the local maximum value. This is what happens. This is when it happens. So what is the local maximum? Approximately 3.83. When did that local maximum occur? When x equaled 2 pi over 3. That's the language that I like to use to make those distinctions. You're not going to see that language match up everywhere, but conceptually, I think it helps to make the distinction between when is a thing happening and what is happening. All right, speaking of what's happening here? We're working with the same function, g. We're still looking at its first derivative, g prime. The derivative is changing from negative to positive, so we're going downhill. That's negative, changing to positive. Uphill, guess what's happening right here? What kind of an event are we going to have right there? That is a local minimum. When does that local minimum happen? When x equals 4 pi over 3. What is the local minimum? Approximately 2.46. And we figured that out by taking the 4 pi over 3 and plugging it into our original function g. All right, and there it is. That is the graph of the original function g on the interval from 0 to 2 pi. And we see that we do have a maximum when x equals 2 pi over 3, and we do have a minimum when x equals 4 pi over 3. Nice to have the visuals to go along with that. Now, check this out. This doesn't say f prime, this says f double prime. What does f double prime say about our original function? Here's a graphical opportunity for us to talk about the second derivative. You can and should read all of this stuff as we go along, but I'm going to try to make some of this stuff more simple. This portion of the curve that we're looking at right here is cupped, maybe you could say, in the upward direction. More formally, we would say, and the author says that they're bent in different ways, right? They bend in different directions. I like to say that this blue curve that we're looking at here is cupped or concave in the upward direction. All right? if you were going to try to capture something with this, or if this were a lacrosse stick or a hockey stick, this is where the puck or the ball are going to end up, right on the inside of the curve, so to speak. So this is the direction that it is concave. And this curve over here on the right, you would say is concave down. And supposedly, I'm guessing that the second derivative of our function is going to help us determine concavity. And it is. You can go through and read this. I read this. I didn't find it the most helpful because you're talking about things that are increasing more, right? Here are the slope of the tangent line is positive, but it's only a little bit positive. And here the slope of the tangent line is even more positive. And here the slope of the tangent line is even more positive. So it's a positive thing getting more positive. What we're looking at here is something that's positive. Oh, I went too far. We're looking at something that's positive, and even more positive. This is, interestingly, this is positive, this is less positive, and this is even less positive. In the first case, we were concave upward. In the second case, we were concave downward. So in both instances, f prime was greater than 0. The slope of all those tangent lines were greater than 0. They were all positive. But one of them was becoming more and more positive, and one of them was becoming less and less positive, but still positive the whole time. So, the definition, finally a definition, if the graph of your function lies above all of its tangents on an interval, then it's concave up, or upward. And if your function lies below all of its tangents on an interval, then it's called concave downward. Well, that's great. As long as you've got a drawing of your function, and it's an accurate enough drawing that you can go in and pretty accurately determine that my function is staying below all of my tangent lines, then I guess this is concave downward. Here I've got a negative sloping tangent line and a negative sloping tangent line at this point. Still concave downward there. But at point B, there's a change. When x equals lowercase b, there's a change. Now, my tangent line resides below my curve. Tangent line here is below the curve, or curve is above the tangent line. So, here we're concave up. This is concave up, concave down. Here we're concave down. That was not an arrow, and so on. Okay? So if you're given a graph, honestly, I trust you. I think you can probably just look at it and determine if it's concave up or concave down. For me, the parts of a graph, or the graphs that are maybe the most potentially tricky, is maybe graphs like this, especially when there isn't already a line in here giving you a hint that maybe concavity is changing. We will need to be, or you will need to be, more careful when you're working with graphs and they're changing concavity right in the middle of a curve like that. How does the second derivative help determine the intervals of concavity? Let's just see. Instead of visually, I'd like to change to something a little bit more numerically based. If your first derivative is an increasing function, then its derivative, in other words, the second derivative, is positive. In 6b, when the slope of the tangent line was becoming less and less positive as we went from left to right, then the slope is actually decreasing. And therefore, your second derivative is going to be negative. So the decreasing is referring to that negative and vice versa. Again, some of you out there are listening and saying, God, it sounds like he knows what he's talking about, but really my head's just hurting. and I think I need to hydrate some more and take some Advil. I don't know if I'm going to make it through this. Just hang in there until we get to actually doing some tests. I think that following the mechanical process of this will be a lot easier for you. And then once you have the mechanical process to go along with it, you can start to make some connections between the process and the concept. Thank heavens, a concavity test. If the second derivative is greater than 0 for all the points on an interval, then my graph is concave upward. Oh, I love it. Greater than 0, concave upward. I think I can even remember that. And if it's less than 0, then it's concave downward. All right, we had to do all that talking just to get to that point, to get to this really easy concavity test. Yeah, well, that's the process of matching up concept with the actual mechanical process of solving problems. So here we're looking at Cyprian honeybees that were raised in an apiary. By the way, Cyprian honeybees, in case you didn't know, Cyprian, that means that they come from Cyprus. If you're not sure where Cyprus is, you should Google it. You should have a little look at a map. Okay, so over what intervals is P concave upward or concave downward? Just visually, I'm going in, I'm looking at this thing, I'm trying to see, this thing's definitely curving upward, this thing's definitely starting to flatten out again, so somewhere there must be a transition between, this is definitely cupped in the upward direction. Maybe I could come in here very carefully and draw some tangent lines. My curve is above my tangent line, my curve is above my tangent line. Boo, that looks right on the tangent line. Here my curve I think should have been below my tangent line. Maybe here? Maybe that's where the change in concavity happens? By looking at the slope of the curve as t increases, we see that the rate of increase of population is initially small, and then it gets larger, and then it reaches a maximum at about 12 weeks. That's the maximum that they're talking about there is the maximum rate of increase of population. And then the population starts to level off. The population doesn't decrease, it's the rate of increase starts to decrease. The rate of increase was initially increasing quickly, and then it starts to decrease as the population starts to level off. Okay. The curve appears to be concave upward on this interval and concave downward on this interval. Another definition. A point P on a curve is called an inflection point if the function is continuous there, so it has to be continuous, and it's where your curve is changing from being concave upward to concave downward. So the definition that you're taking in your handwritten notes says that an inflection point is where your function is continuous and where you're changing from concave upward to concave downward. And that point P is called an inflection point. Great. So suppose our second derivative is continuous near some particular point, and the first derivative at that point is equal to 0, or rather, if the first derivative is equal to 0 at that point, remember, which means we have a horizontal tangent line, and the second derivative is greater than 0, then we're looking at a point that has a local minimum. This point, right here, first derivative equals 0, horizontal tangent line. Second derivative is greater than 0, which means concave up at that point. And then similarly, we could be looking at another point, except it would be concave down if the second derivative were less than 0. Oh good, finally an example. Whew. So let's look at this function, y equals x to the 4 minus 4x to the third. It might be helpful to you. to have an image of what that function looks like. So, okay, it's kind of weird looking. Great. Okay, so let's discuss the curve with respect to concavity, inflection points, maxima and minima. Okay, let's have a look. So we've got our original function, and in order to find maxima and minima, at least potential, we're going to need to find out where the first derivative is equal to 0. So we're going to need to take the first derivative, and then when we start talking about concavity, we will need the second derivative. So there's our second derivative. Both the first derivative and the second derivative have been factored for us. That's nice. So we might refer back to those. In order to find the critical numbers, we're going to take the first derivative and set it equal to 0. So remember, that's places where we've got horizontal tangent lines, which could be at the top of a curve, could be at the bottom of a curve, which would be a minimum, and then it could also be at a point like this, where we don't actually have a max or a min. However, concave down, concave up. First derivative here is equal to 0. What's the second derivative equal to at that point? Interesting. We're going to use the second derivative test in order to evaluate those critical numbers for concavity. So, let's see here. First derivative, setting it equal to 0, gives us two x-coordinates, x equals 0 and x equals 3. Let's take those x values, right? So those could be maximums, minimums, or neithers. Let's plug them into the second derivative test and find out if we can immediately tell something about concavity. We take the x value of 0 and we plug it into our second derivative, and we get an answer, so to speak, of 0. What does concavity 0 indicate? Since the second derivative, when x equals 0, returned a 0, the second derivative test gives no information about that critical number. So how am I supposed to make a determination about what's going on at that point that has an x-coordinate of 0? Well, we can go back and look more closely at the first derivative. Since the first derivative was negative, in other words, the slope of the tangent line was negative, the function's decreasing to the left of the point where x was equal to 0, and to the right of the point where x was equal to 0, right? So we are decreasing to the left of that point, and we're decreasing to the rest of that point. Then we can draw the conclusion from the first derivative test that says the function does not have a local max or min at the point with an x-coordinate of 0. However, there was that other x-coordinate, the x value of 3. The second derivative, when x equals 3, was positive, which means that our graph is concave up, which means it's going to have a local minimum at a point that has an x-coordinate of 3. What does this next slide say, if anything, about that point? Nothing at the moment. What's happening next is we're sort of transitioning into this bottom part of the slide where, since our second derivative was equal to 0, when x equals 0 or 2, we can divide our number line, or sort of chop up the x-axis into intervals using those numbers as endpoints. So we're looking at everything to the left of 0, between 0 and 2, and to the right of 2. And if we plug some sample values from those intervals into our second derivative, we find out some information about concavity. Wow, so how are we're supposed to use all of this information to get a better idea of what this graph is, having never actually seen this graph, although I've scrolled down and showed it to you before we even started this problem. The point 0, 0 is an inflection point since the curve changes from concave upward to concave downward. We saw that here. Here's the point 0. To the left of it, we were concave upward. To the right of it, we were concave downward. So if you're changing from concave up to concave down, that point of transition is an inflection point. And then that happened again when x was equal to 2. We changed from concave down to concave up. Concave down to concave up. Concave down to concave up. That's a little drastic, but you get the point. The point where you're changing concavity here had an x-coordinate of 0, here has an x-coordinate of 2. Those are our inflection points because the curve changes concavity. Also, that point that has the x-coordinate of 2 just so happens to have a y-coordinate of -16. It's an inflection point since it's changing concavity. And using the local minimum, the intervals of concavity and the inflection points, we can sketch this curve. So we saw that the interval to the left of x equals 0 was decreasing and that it was concave upward. We saw that from 0 to 2, I'm talking x values now, we were concave downward. The function was still decreasing, right? So decreasing, decreasing. Even though this point right here, which turns out to be 0, 0, does have a horizontal tangent line, it was not a maximum or a minimum. And we had to confirm that because, or we confirmed it by looking at the fact that our function was decreasing on the left of, to the left of this point and to the right of that point. Then we took this interval which stopped at 2 because we had another inflection point. Concavity here changed to be concave upward. Our function was still decreasing. On this interval to the right of our x value of 3, our concavity still concave up, but we change from decreasing to increasing, and it's that change on a horizontal tangent line there. So changing from a negative slope to a 0 slope to a positive slope told us that it was a minimum. We didn't actually have to do all of that work in order to realize that this point was a minimum because the second derivative at that point was greater than 0, so we knew that it was concave up even there, and therefore that it was a minimum. Over here, we had to do additional investigation because while the slope of the tangent line here was 0, the second derivative, which is supposed to tell us about concavity, the second derivative came back not as being greater than 0, not as being less than 0, but as being 0. So the second derivative did not give us any information about the curve being concave up at that point, nor being concave down at that point. So we had to go in and do some additional investigation to figure out exactly what was happening. And the additional investigation, again, was done using the first derivative. And then, of course, you could take all those x-coordinates and you can plug them into the original function in order to generate y-coordinates, and then you can plot some points, and you got yourself a graph. I made that sound really easy, right? Well, it's huge, and all of a sudden you've got a graph. That's what graphing calculators are for. This is something that we were just talking about, the fact that the second derivative test is inconclusive when the second derivative is equal to 0. That's what happened here. Second derivative was 0. Might be a maximum, might be a minimum, could be neither. That second derivative test also fails if your second derivative turns out it does not exist. So you'd probably have to be working with, or maybe would definitely have to be working with fractions where your variable is in the denominator, maybe a logarithmic function or something. Right here, here's a second derivative function. Plug in an x value of 0 right there. What's your whole denominator turn into? 0. What's negative 8 divided by 0? Undefined. So there's an example where a second derivative test could, or the second derivative test could kind of fail you. And then you'll have to manually go in and do some additional investigation. But in this example, we've got this super fun looking function here. Thankfully, the author has given us the first and second derivatives already. And when the first derivative is set equal to 0, we get an x value of 4. And we have to notice that the first derivative does not exist when x equals 0 or 6. 0 would turn this factor into a 0. Positive 6 would turn this factor into a 0, which would give us a denominator of 0, which causes division by 0, which is undefined. And when your first derivative is undefined, that's a point of interest. So those become critical numbers also, 0, 4, and 6. You want that to be in your notes. Any place, or rather any time, any x value that causes your first derivative to be 0 or undefined is a point of interest, in other words, a critical number. So we take and we chop up the x-axis into 4 different intervals using our 3 x coordinates, and then we go through the motions, investigating, increasing, and decreasing by calculating not the exact value of our first derivative function, but rather the sign of our first derivative function, whether it ends up being negative, positive. It's not going to be 0. We already know when it turns into a 0 at 0, 4, and 6. So we're only going to be coming up with positives and negatives here. That tells us decreasing versus increasing. If here I'm decreasing and here I'm increasing, what kind of a point are we talking about? If I'm going downhill and then all of a sudden I start going uphill, what kind of a point is this? I vote for a minimum. If I'm increasing and then I start decreasing, I've hit the top of a hill, probably talking about a maximum right there. Decreasing to decreasing, and I'm walking downhill, and I get to take a rest at this point where it just so happens to be flat for an instant, and then I'm decreasing. So when I'm changing from decreasing to decreasing, this is going to be not a very eventful point. Okay, good spot to take a rest, take a picture, maybe take in the view. Maybe you've got some mountains out here, or ghosts, or I don't know what those are, but yeah, not a maximum or a minimum. So this is the conversation about making those evaluations that we just talked about. You could use the second derivative at the x value of 4, but not at 0 or 6, since the second derivative does not exist at either of those values. But you could use the second derivative test when x equals 4. When x equals 4, that's between these two intervals. And what's happening between those two intervals? You're changing from increasing to decreasing. And we just talked about what happens when you change from increasing to decreasing. Got yourself a maximum. All right, let's pop down to this next slide, looking at the expression for f double prime and noting that this is greater than 0 for all x values, and that our second derivative is going to be less than 0 for all of our x values that are less than 0. And in here, we're concave up for x values greater than 6. We're using all these little pieces of information in order to get a better feel for what the graph is going to look like and what kind of changes are happening and how fast they're happening. So, excuse me, so from looking at the second derivative, we can tell that our function or our curve is going to be concave downward to the left of 0 and from 0 to 6. Concave down, and concave down, and concave upward to the right of 6. And the only inflection point that we have is at 6. What's an inflection point again? Where our concavity is changing from concave downward to concave upward. And where does that change happen? Or when does that change happen? When you've got an x value of 6. That transition from this interval to this interval. And here's a graph of our function. I was taking a stab at trying to graph this for myself. I'm trying to think, how does it go from being concave downward on this interval and then immediately concave to another interval? Like, I get it that at 0, it's neither, right? Because there are parentheses next to those zeros, so it's not concave up or down at 0 that we know of. So how do you change from concave down to concave down? Boy, does having this graph really help. Here we are to the left of an x-coordinate of 0. That curve is definitely concave down. Here we are to the right of an x-coordinate of 0. That portion of the curve is also definitely concave down. And then here we are at our local maximum, where f prime was equal to 0. And f double prime was less than 0. In other words, concave down at that point. So we were concave down here, and we're concave down here. And then there's our other inflection point, which happens when x is equal to 6. And what's an inflection point? We're changing concavity. Concave down here, concave up here. In your study of maths, your graphs probably didn't look like this. That is an unusual one, to be sure. And then to now have the vocabulary and the processes to go in and dissect it and know even more about what's happening in this function and when the various types of changes are happening, that's some really deep understanding and knowledge of these curves. The next big step, of course, would be applying these to real-world situations, designing equations to model real-life events, which is called modeling, and that is some challenging stuff. Something to aspire to, perhaps. Right, that is enough about this section. I thank you so much for hanging with me through this conversation. I almost forgot to work example problems for you. So, let's look at this one from a web assignment that I'm going to be assigning to my students. This is an assignment that matches up with material from Stewart's calculus book and that we were just looking at slides from. And in this problem, we're given the graph of the derivative of a function. This is not the graph of the actual function. And the question, part A, is on what intervals is our function increasing? And remember from the slides that we were just looking at, a function is said to be increasing on an interval where the derivative is greater than 0. Let's put a little arrow for increasing. And it's decreasing if the derivative is less than 0. So remember that the derivative can be interpreted as the slope of the tangent line. So where on our graph over here is our first derivative greater than 0? Yet another way to interpret this statement is where is our function that we're looking at here, f prime, right? This is f prime. Where is our function greater than 0? Where where does our function reside above the x-axis? For example, let's say that this has a y value of 1. What is f prime of 0.5? F prime of 0.5. What do you think? What's f prime of 0.5? In other words, what do you think the y coordinate is right there? I think it's probably, I don't know, 0.9. 0.9. So can we safely say that the first derivative at that particular point is greater than 0? 0.9 is definitely greater than 0. So what that means is that our actual function, which is not depicted here, has a positive slope at a point when x equals 0.5. Alright, so let's not overcomplicate this. On what intervals is f increasing? It's increasing on the intervals where f prime is greater than 0. When is f prime greater than 0? It's greater than 0 on the interval that goes from 0 to 1. That's an open interval, so we're using parentheses or open brackets, we call them. Also, on the interval that goes from 3 up to 5. And those are the only two intervals. Here and here. Notice that those are the two parts of the graph of f prime of x that are above the x-axis. They have y values that are greater than 0. On what intervals is f decreasing? It is decreasing on intervals where f prime is less than 0. In other words, where the graph of f prime is below the x-axis. That would be from 1 to 3 and from 5 to 6. Is it possible that the answer to this question, because this circle is colored in right here, it's a closed point, is it possible that that means that this should actually be a closed bracket? In other words, a square bracket? It does look to me like f prime of x, or f prime, is actually less than 0 at that point. F prime of x looks defined at that point, so perhaps that should be a square bracket. It is also, therefore, possible that this closed circle with an x-coordinate of 0 should cause this to be a closed bracket, because that point there that has an x-coordinate of 0 does for sure have a y value that is greater than 0. Therefore, the function should have a positive slope there. So be sensitive to that from software to software and professor to professor. You're going to be asked to answer these questions in very certain ways for hopefully very specific reasons. Part B, at what values of x does our function have a local maximum or minimum? When does a maximum happen again? What does a maximum look like? Well, if our original function looked like this point right here would be the maximum, and to the left of that point our function is increasing, and to the right of that point our function is decreasing. In other words, f prime is positive here and f prime is negative here. So where are we changing from having a positive f prime to having a negative f prime? I think that happens where our x-coordinate is 1. At this point, to the left of it, f prime is positive or above the x-axis, and to the right of it, f prime is negative or below the x-axis. So I would say, at what values of x does f have a local max or minimum? So we're entering our answers as a comma-separated list. I'm going to go with 1 as my first x value. And switching from negative to positive, that means that this point would be a minimum. So that's an x-coordinate of 3. And lastly, changing from positive to negative again at an x-coordinate of 5. All right, those are the solutions to this version of question number 3 anyway. Let's see if we can toggle over to question number 4. All right, I don't know why there is a line already on this page. Let's see if we can get rid of it. Sure can't. That's okay. All right, in this question, we're considering the equation below. This is a function, and we want to find the intervals on which the function is increasing. Now, I only have a limited space over here, so I'm probably going to be writing out some stuff and then erasing it in order to continuously sort of recycle that space. Find the intervals on which the function is increasing. How do I know where it's increasing? I need f prime to be greater than 0. All right. That means I need f prime. Let's figure out the first derivative of this function. F prime of x equals 4 times 3 is 12 times x, decrease the exponent by 1, plus 2 times 6 is 12 times x, decrease the exponent by 1, it becomes a 1, minus 1 times negative 24 is negative 24, decrease the exponent by 1, derivative of a constant is 0. Great, this is our first derivative. Let's also factor this like your author did. So let's factor out the 12. That leaves us with x squared plus x minus 2, and then factor it one step further. 12 times x plus 2 times x minus 1. This is f prime. And the next thing we're going to do is set it equal to 0. We'd like to know where we have our horizontal tangent lines. When does f prime equal 0? And then on either side of those 0 values, we should find f prime values that are either positive or negative. So the points of interest, or the x values of interest, are an x value of negative 2. That would make that factor equal to 0. And an x value of positive 1. That would make that equal to 0. I'm circling these just so that they don't wander off. I'm not putting a box around them. I'm not writing them down over by our text entry box over here, okay, because these are not final answers yet. What they do is they help me chop up the number line, and I think I might just put a number line right through there. There's an x value of negative 2. There's an x value of positive 1. Let me see if I can do some very specific erasing here. That's nice. Very good. Okay. Your author did this in a table. I'm going to do it just here on the number line. I'm going to test an x value that's on this interval to the left of negative 2, and I'm going to test an x value that's in this middle one, and I'm going to test an x value that's in here. Maybe we'll test x equals negative 3, and x equals 0, and x equals 2, and we'll see whether the slope of our tangent line, f prime, is positive or negative. All right, let's take negative 3 plus 2, still negative. Negative 3 minus 1, still negative. Negative times a negative makes positive. Let me do that better. A negative times a negative makes a positive. Now let's plug in the 0. Zero plus 2, positive. 0 minus 1, negative. Positive times negative, negative. So our function is going to be decreasing there with a negative sloping tangent line. And lastly, two plus 2 is 4, which is positive. 2 minus 1 is 1, which is positive. Positive times positive makes positive. so the slope of our tangent lines are positive there. F prime is greater than 0. Terrible handwriting, all true statements, however. F prime is greater than 0, F prime is less than 0, F prime is greater than 0. As we change from a positive slope to a negative slope, positive slope to a negative slope, what is happening in between? We've reached a max. And when we transition from a negative slope to a slope that's greater than 0, a positive slope, what's happening there? There's a minimum there. So finally, well, we weren't being asked that just yet, so let's not get too far ahead of ourselves. Part A, find the intervals on which the function is increasing. That is everything to the left of x equals negative 2. Right, we were increasing there. So we can answer from, why isn't this writing? There we go, from negative infinity all the way up to negative 2. And is it increasing anywhere else? It sure is. Everywhere to the right of x equals positive 1. So we're starting at 1, excluding the 1 with an open bracket, going all the way up to positive infinity. Find the interval in which f is decreasing. That would be the middle interval, where we tested an x value of 0. So those are the x values that start at, but do not include negative 2, going all the way up to an x coordinate of 1. Find the local minimum and maximum values of our function. Well, what we're looking for here are y values. We don't know the y values, but we know when those y values occur. Those y values occur when, for a local minimum, that y value occurs when x equals 1. So we need f of 1. Not f prime of 1, but f of 1. That's going to equal 4 times 1 cubed, which is 4, plus 6 times 1 squared, which is 6, minus 24 times 1, which is minusing 24, and then adding 5. So I've got 10 minus 24, which makes negative 14, plus 5, which makes negative 9. If my arithmetic is correct, which it is not always. Our maximum occurs when x is equal to negative 2. So we need to evaluate f of negative 2. Which I would calculate by carefully typing segments into a calculator. You've got 4 times negative 2 cubed, which is negative 32. You've got negative 2 squared, which is 4 times a positive 6, so plus 24. You've got negative 24 times negative 2, which is positive 48, plus 5. These two values add together to make positive 16, 40, 45. So that is your local maximum value. It happens when x equals negative 2, and your minimum of negative 9 happens when x equals 1. Find the inflection point. What's an inflection point? An inflection point is where we change concavity. How do I, or what am I using to calculate concavity? We're using the second derivative. So I'm going to erase, as I said, a bunch of things over here on the right-hand side of our screen. So that is our first derivative, and I'm going to switch colors in order to calculate my second derivative. F double prime of x will equal 2 times 12 is 24 times the x, decrease the exponent, plus 1 times 12 is 12, decrease the exponent. We've got 24x plus 12. An inflection point is going to happen where, now, I know that I'm working with a polynomial. Polynomials are smooth and continuous everywhere. I don't have to worry about asymptotes or holes or any sharp corners, anything like that. So I don't have to worry about my second derivative being undefined. But what I do need to figure out is when is my second derivative going to equal 0? In other words, where is my function neither concave up nor concave down? If I subtract 12 from both sides, and, well, I'll write out that step. 24x equals negative 12, x equals negative 1/2. This is when I might be changing concavity. So on my number line, here's x equals 0, here's x equals, I don't need to write the letter x equals negative 1/2, and if I'm going to be changing concavity, then let's look at what's the concavity when we are to the left of this point and what's the concavity when we're to the right of this point. So let's do a couple of quick calculations. To the left of negative 1/2 would be negative 1, so f double prime of negative 1 is equal to 24 times negative 1 is negative 24 plus 12 equals a negative value, negative 12. I don't even care that it's negative 12. What I care is that it's less than 0, which means it's concave down. And then let's test an x value that's to the right of negative 1/2. How about 0? So what is f double prime of 0? That is 24 times 0, which is 0, plus 12. I don't care that it's 12. I care that it's greater than 0, which means it's concave up. So we're changing from being concave down to concave up, which means that that is an inflection point. And when does it happen? It happens when x equals negative 1/2. Find the inflection point. We know that the x-coordinate of the inflection point is negative 1/2. Oops, that is the wrong writing utensil. Let's stay in blue. Negative 1/2. And the y-coordinate there we have to find by taking negative 1/2 and plugging it into our function. So we need f of negative 1/2. I'm going to go off to the side and do those calculations and just tell you that f of negative 1/2 equals 18. So our y-coordinate there is 18. That is our inflection point. Find the interval on which our function f is concave up. We determined using a test value that our function was concave up, testing an x value of 0, which was to the right of negative 1/2. So the interval on which our function is concave up starts at but excludes negative 1/2 and goes all the way up to positive infinity. Where is it concave down? Concave down was when we tested the x value of negative 1/2, negative 1, which was to the left of negative 1/2. In other words, we are concave down from negative infinity all the way up to negative 1/2. That is the process of tearing apart at least a polynomial function and making decisions and determinations about where the function is increasing and decreasing, using information about being increasing and decreasing in order to decide where your local maximums and minimums are. That was supposed to be an arrow. There we go. And then taking a second derivative in order to find your inflection point. And the inflection point is sort of the separator between the intervals where you are concave, in this case, down, and concave up. Just realize that you could have an inflection point where you're changing from concave up to concave up, or down to down, but that function or that equation is going to look substantially different than the one that we were just working with. Thank you so much for examining these couple of practice problems with me. I hope that they were helpful, and I look forward to seeing you, so to speak, in the next video. Thanks so much.